And thank you. Oh, uh-oh.
Oh, dude, I forgot I said that out loud. Sorry.
Well, I'm not gonna do it over, but thank you so much for being here with us. And take it away.
All right, thanks so much, Kanti, for that introduction, and thanks to the organizers for inviting me. It's really a pleasure to be here with all of you today. So let me try to share my screen. Oh, so host disabled participant screen sharing. Can somebody let me share my screen?
You should be able to do it now. Sorry.
Okay, let me try again. Yep, let's see. Okay, so I'm going to ask the question we always ask, which is, does everybody see my screen?
Yes, you're good.
Good. Okay. All right, folks. So I am going to attempt to give you a 1.5 introduction to deep learning. So this is something that, of course, takes something that you can spend, a couple of semesters doing, right? So of course, this is not going to be very in depth, right? This is going to be, I'm going to try to give you a high-level overview and to kind of give you some breadth of a vision of the field as opposed to depth, right? And to give you some nice kind of some indications of where you might want to dig into for further understanding. Okay, and so this lecture is divided into 2 parts. So I'm going to give the first lecture, and then Roseanne Liu will give the second lecture tomorrow, I believe, with a focus on NLP. And here I will give kind of like a general introduction to deep learning, also with a focus on computer vision. Okay, so with that said, let's get started. So here's like the brief agenda for the next 1.5 hours. So I'm going to kind of just introduce the concept of deep learning. What do we really mean by that term? Then I will talk about how do we design deep models before going into how do we sort of estimate model fit using loss functions. I think it'd be a good idea to stop for like a quick 5-minute break / Q&A session at this point. And then after that, we'll go into how do we optimize these deep models? So how do we actually do some learning? And then I'll close off with giving a few like representative applications of deep learning applied to computer vision problems. And so in terms of, and so at the end, I've left a bit of time for questions, so we can do that. So what I would suggest is that we keep all the questions for like the kind of midpoint Q&A and the end. Unless you have like a really burning question, then feel free to raise your hand. Okay, and so before we start, so just a brief note on notation. So vectors are going to be in bold lowercase. We're going to have matrix variables in bold uppercase, and scalar variables will be in lowercase. Oh, I just need to shift this a bit so that I can see all of my slides. Okay. Right, so let's get started. So what is deep learning? So I'm just going to break it down, basically the term, right? So we have 2 terms. So a deep learning model is deep. So what does that mean? So normally you can think of it as a computational graph. And this graph is normally a directed acyclic graph. So it means that there are typically no cycles, although this is not always the case. And it's typically directed, right? And so it's a computational graph where these computations are parameterized. So they have parameters, and very importantly, these parameters are learnable parameters. So if we kind of look at our sort of toy example here, where you have y as a function can be described, it's computed by basically applying this function f parameterized by w to x. And it's, like this sort of like nested set of functions. We can think of this as the sort of the computational graph you see here, where this is like a very simple directed acyclic graph, where we have these intermediate computations or representations, you can say, of x, which eventually give you some output value. So that's the deep part, right? So the deep implies basically that you have this sequence of computations, and these computations are non-trivial in the sense that you can't sort of, you can't reduce them to sort of like a simple computation. And so the second part of the phrase is learning, right? And so that comes into the fact that these computations can be optimized in order to approximate some type of function. So for example, looking here, right? So we have on the top, we have y, which was this output, right, of the series of computations. And what we would like is that y is approximately equal to some target, right? So to say it another way, we would like to learn f parameterized by w such that it's equal to, or it approximates well, some function of interest, right, f star. So of course, we don't expect to have an analytical expression for this function f star. What we do have access to are training samples. So these training samples are normally in the form of input-output pairs, right? So we have xi with some sort of target, right? So you can think of this as an input and then the output that we want with respect to this input. And this is basically what we're going to use to estimate our model. Okay, so we're going to have some model f, some deep model, right, with a series of computations. They're going to be parameterized by parameters w, represented by this vector here, w. And then we have these training samples that we're going to use to estimate the values of w. And so that's deep learning in a nutshell. You heard me use before the term representation learning. So why use this term? So if you look at this series of computations, you can see that there are intermediate results, right, all throughout the graph of computation. So for example, I'm showing you one here where we have, some intermediate result, which you can term O1. And this is often called a representation of the input X, right? Because you can think of it as some sort of transformation of the input signal. And so when the parameters of these mysterious functions, right, when they're optimized, the representation is said to be learned. Okay, so we have a deep model. We want to use it to approximate a function. So what kind of functions are we interested in approximating? So this is why deep learning is very useful, because we can use it to approximate extremely complex functions. So to give some examples, one very canonical example is image classifiers. So in this case, we might want to learn a function that can make a mapping between an input image and some sort of a class, basically, or category, so to be able to label that image. So in that case, what we want to learn is a function that gives us a probability of an input belonging to a specific class. And this can be very complex. So you can have, for example, the famous case of ImageNet has, in one instance, 1,000 categories, or if you want to go even larger scale, there's a version of ImageNet with even 10,000 categories. So you can imagine having to model this implies modeling a very complex function. We also want to estimate a function f, where this function is taking as input some image at time t, and you want to be able to output what the subsequent, let's say, image in a sequence would be, right, t+1. So this, you can consider this like a video generator, right, that is giving you, given a specific image, what would be the most likely next image that you would see. You can also do speaker identification. So let's imagine you have as input to a function, like sort of like a snippet of speech. You'd like to be able to know who does this belong to. So let's imagine you have, maybe 20 people who might possibly be speaking. You want to categorize this speech as being spoken by one of a certain number of possible speakers. Also, you can use it for shape reconstruction models. So let's imagine your input is a point cloud, as you're seeing here. You would like to be able to predict or to model the geometry of this point cloud, right? So to be able to understand, like, what's the shape of this. You can also do text understanding, of course. So given a sequence of text, you like to be able to understand, is this, for example, text expressing a positive sentiment or something negative? You can also use deep models to model link prediction. So let's imagine you have a social network and the social network wants to recommend to you, to a user, potential friends, right? So you can consider this recommendation of a potential friend as recommending a link in this social graph. And lastly, so we have, as you guys might have heard, recently about the news of AlphaFold, where this is basically a model, a very powerful and very impressive model that given like a sequence of input proteins, a sequence of proteins, to be able to predict like the 3D shape of this protein. So, what I want to show you here is basically with all of the sort of fairly simple building blocks I'm going to show you, you can use this along with examples to train extremely complex and effective function estimators. So we mentioned that these models are deep, so they're supposed to be like a sequence of computations that can't be reduced to just one single computation. So why is this interesting? Why is this a useful or an interesting way to represent models or to build models? So number one of the reasons that the field went in this direction was because of biological inspiration. So, deep model has a strong basis in artificial intelligence, and when the field was quite nascent, of course, we looked to biological inspiration for understanding how to represent and compute and gain understanding from perceptual inputs, right? And so one specific source of inspiration was, of course, the human visual cortex. And convolutional nets in particular were heavily inspired by studies of the visual cortex, in particular with the fact that a lot of cortical processing is very hierarchical in nature. And as you'll see, this is also a hallmark of deep learning. The fact that basically you have an input signal and then you apply to it progressively complex and hierarchical computations. So that's sort of like one avenue into the concept of and the interest in deep learning and deep models. And the other one is expressivity. So coming at it from a different angle, convnets and other types of deep nets implement highly nonlinear functions, right? And so with this nonlinearity, this results in extremely complex and flexible and expressive models, which is what you need in order to learn the types of very complex functions that I was just giving examples of earlier. Okay, so that's a brief overview of what is deep learning and why is it interesting, and why is it like an interesting avenue in order to explore learning complex functions. So let's sort of dig into kind of how they're built. So I'm showing you here once again this toy example. Okay, so what are these? What can be potentially some of these mysterious functions like F2, F1, etc. So as complex as deep models can be, and your average deep model these days can have dozens or hundreds or even thousands of layers, and this might be a bit surprising, they tend to be built off of really 4 or 5 basic building blocks. And I'm going to go through each of these in turn, starting with fully connected layers, going on to convolutional layers, pooling layers, and activation layers. Okay, so we're just going to go through these one by one and sort of get an understanding of them. So fully connected layers. So what I'm going to do is just literally go through an example of this with you. So I believe you guys have been familiar with linear algebra, and I think you got like a bit of a refresh yesterday. So this is really a simple dense multiplication, okay? Like a vector matrix or sometimes matrix multiplication. So a fully connected layer is basically implemented with this function, this equation here, right? So you have some sort of vector of like an input vector x. You apply to it, a matrix multiplication, and then very often there's a bias term, a bias vector, and this gives you your output vector. Okay, so if we break this down, then you can see that each element in hi, will be simply this linear combination here. Okay, so let's imagine we have this very toy example here of an input vector of length 5. Then to compute output 1, you're going to multiply by 5 weights, right? And then this gives you h1, and you do some analogous computation, and then you get your output vector. So it's really that simple. Okay, so moving on to convolutional layers. There are quite some similarities with linear layers. They're with fully connected layers. They're also linear layers. Some of the motivations of using them in place of fully connected layers are that they have sparser connectivity in general. It allows us to, convolutional layers have a lot of weight sharing in general. So you can, I will show you why this is interesting later on. Also, convolutional layers, they're very local operations. So this allows you to encode a lot of inductive bias about translation equivariance into your model. And I'll show you that later as well. And lastly, it allows us to work with arbitrary input sizes, which will be quite interesting for several applications. So I'm going to go through an example of this as well. But before that, let's introduce the actual concept of a convolution, okay? Because this is basically the basic computation that's happening in these layers. So I'm going to give you like a 2D example, usually a 1D example, but this, the signal dimensionality is arbitrary. And in most deep networks, they will often be, they'll be performed in 3 or even 4 dimensions. So this is the standard, definition of a convolutional operation, right? So you have 2 input signals, input signal I and input signal K. So K is normally called a kernel or sometimes a filter. And so a convolution is an it's an operation over 2 signals that gives you an output signal. And if you just look at the first equation here, you can see that what it's doing is it's taking your input signal I, you're multiplying it with a shifted version, right? Shifted by I or j of your input kernel K. And this kernel K, as you can see, it's flipped, right? So you're taking your input I, you're taking K, you're flipping it, and then you're integrating over the product of the 2 signals, right? So you can see that's what this is happening here. And then what you're doing is you're summing that integral over different shifted versions of K. And then what you're seeing in the second line is just showing the fact that this is commutative. So basically the convolution of I and J is the same as the convolution of K is the same as the convolution of K with I, okay? So that might not be super intuitive. So let's just take like a super trivial example just to show you what's happening. So let's imagine you have your input I here, this little square function, and then you have this function here, K. So a convolution of I with K is going to simply take your signal I. It's going to flip your signal K. So you can see K, the triangle is in the other direction now. And you're going to shift K with respect to I, right? So here we're showing 5 examples where you have K quite to the left, and then it progressively is shifted to the right, okay? And at each position of K, you multiply the signal K, the shifted and flipped version, with your signal I, and then you integrate over it, right? So you can see that in this example here, because there's no overlap of non-zero support, your output value is 0. And you can see that as you shift K further to the right, you start to go from having 0 overlap to starting to have some overlap until it peaks, and then it goes down. Okay, so that's basically what a convolution is doing. And what you'll see is that what this is actually doing is it's doing some version of pattern matching. It's giving you a sense of what resonance does their signal I have with your kernel A at localized positions as you shift K, okay? So one point to note here is that convolutions are defined with respect to infinite signals, okay? And generally, when we're working with things like images, for example, or just in general, most of the signals we work with aren't infinite, right? We don't have infinite images. But what we do to handle that is that we know that there's a certain point when you shift your signal too much, that the signal has no more support, it's not defined. And so typically we do what we call padding. So we pad it with, for example, zeros. So one thing that's maybe not intuitive is that actually for convolutional layers, Typically, we don't use convolution exactly, but we use like a very related concept called cross-correlation. So I'm going to show you, compare the two of them now. So the first line is the convolution I just showed. Cross-correlation is very similar. The only difference is that we're not flipping the kernel, right? So you can see here the k is not flipped, it's just shifted. So in this case, what the correlation is quantifying is, once again, like a pattern matching. So it's showing you at a local level of signal I, how similar it is to your kernel, okay? And so why is this typically used instead of convolution? Like, number one, we don't care about commutativity, right? So that's one big difference between convolutions and cross correlations. And it's not really a value to us. It's not a property that is very important for us in ConvNets. And, you know, avoiding flipping the signal just makes it easier to implement. So this is why people tend to use cross correlation. But, you know, the function operations are quite similar. So just to compare them very briefly, so, you know, we have our previous example here. And cross correlation, as I mentioned, so we're going to perform pretty much the same operation. The only difference is that we see here that k is not flipped, right? So the triangle has not changed direction, but the operations are quite the same. And you get sort of like a similar output. Okay. So now let's give you a 2D example. This will take us even more close to like a typical real world example of, for example, using convolutional nets for images. So let's imagine you have your input signal here, I, right? You can consider this to be like a very small image. And you want to compute the cross correlation with a kernel K. Okay, so this can be, you can think of this as pretty much your typical 3x3 filter in a ConvNet. And so if we wanted to compute the output, so the convolution or cross correlation in this case, at a specific location, we would just make this computation here, right? So I 0, 0, K 0, 0, etc. Right, which gives you this output value of 1.
There's a question on the previous slide.
Sorry, I don't see it yet.
No worries. I'll step in and I'll let you know. The question is, what is the benefit/importance in not flipping K?
So there's not actually, that's a good question. So there's not a benefit. So which is why we use cross correlation, basically, because convolution has a nice property that it doesn't matter whether you convolve I with K or whether you convolve K with I, which is useful for many applications, but it's not useful for convolutional layers, for convolutional networks, which is why in this case, there's no benefit, which is why in this case, it doesn't matter if we flip it or not. Okay, so actually in this, when we implement convolutional layers, we use cross correlation instead, because we don't have to do this extra step of flipping the signal, which just makes implementation easier. Does that answer it? I'm going to hope so.
Yep, that answers it.
Awesome. Okay. So we can see cross correlation as a sliding window operation. Sliding window being that we're moving, we're sort of sliding the kernel K over a signal I, right? So let's take a look at what this looks like. So once again, we have our input signal, we have our kernel, and I just gave you an example of computing the output at this specific position of K. And so this gives you this output here, 1, right? And so as you shift K, right, so you shifted it by 1, then you see you have to make a computation over this new kind of window here. And it's exactly the same computation. So you multiply, you do this integral of the product, right? And this gives you this value 4. And you just continue. So you continue to shift your K, right? And as you do, you make this computation. And it's as simple as that. And then this gives you this output. Okay, so for those of you who are already fairly familiar with ConvNets or have used them in the past or read about them, you'll know that there's often a term used called a feature map. So this is what is being referred to. So a feature map is this output of the convolutional, or to be more precise, like the cross correlation operation. And so specifically with when we're using examples in computer vision, typically we sort of like visualize these outputs using some sort of heat map like you're seeing here, right? So just basically scaling the response or the output from black to white, where white indicates sort of like a high response. And so here you start to see where the concept of pattern recognition comes in, right? Because if you look at the input here, with the cross correlation computed with respect to this kernel here, and you look at the output, you can see that it gives you some indication of where in the input signal did you see a similarity with this kernel, right? So you can see that, for example, in the upper left corner, it's not very similar to this signal. And so there's a pretty low value. Whereas if you look at the top right, or if you look at the middle, you see that it's more similar. So this is where convolutional operations allow you to sort of perform this pattern matching operation. Okay, so that's basically convolutions and convolutional layers in a nutshell. There'll be a few more details I'll show after. But what I wanted to do now is to kind of show you some of the advantages or the benefits of convolutional layers as opposed to fully connected layers, which we saw earlier. So this is, once again, here I'm showing you the example I showed before, like a very simple example of a very small fully connected layer. So let's do the same for a convolutional layer. So this is once again like a trivial 1D example. And so you see here, you see already one difference, which is that H1 here is not necessarily a function of all of the input values, right? This is why it's not fully connected. It's sparsely connected. Okay, and so if we compute it here, this is how we would compute our output. And as I mentioned before, we can perform something called zero padding in order to deal with the fact that we have inputs of finite size, okay, to give us a full output if we want. So as I mentioned before, with fully connected layers, this requires dense connectivity. So for every output, this output is a function of every input value, right? Whereas with sparse connectivity, it's not necessarily the case. So for example, if we look at output H2, it's not a function, for example, of X4 or X5, right? So this is where sparse connectivity comes in. And so in our example here, this requires for a fully connected layer 5 by 5 multiplications, whereas for a fully connected layer, sorry, for a convolutional layer, you only need 5 by 3 multiplications. So already you see that one advantage of, in this case, of a convolutional layer is that there are fewer computations. So it's in general less computationally expensive. It also scales better. So let's imagine you had an output layer that was 25, right? So you had H of dimensionality 25. This would require a 25 by 25 set of computations, or connectivity, I should say, whereas for the convolutional case, it would be 25 by 3. So it simply scales better. And another point is weight sharing. So once again, in our example for the fully connected layer, we have 5 by 5 weights, right? So we have 5 weights here times the 5 outputs that we want. Whereas for a convolutional layer, we only have 3 weights, right? Because these weights are shared across all of these outputs. So H1 is computed as the weighted sum of the product of the dot product between your input, your local input region, and your kernel. And the kernel doesn't change, right? So this is like a 1D kernel you can think of with 3 values. And this kernel is shared and is just shifted across the signals. So we don't need to have separate weights for every output that we want. And you can imagine this scales way better, right? So let's say that we want to have an output dimensionality of 25. For a fully connected layer, we need to have 25 by 25, whereas for a convolutional layer, we'd still just have 3. So it scales much better.
There's a question, how is the kernel determined?
Yeah, so that's a good question, and it requires a lot of domain knowledge, basically. So the size of your kernel, it's a function of the degree of local information you think is important to capture. right? So let's imagine you think of the kernel as a pattern matcher. So you're trying to say in this local region of my image, I want to match it to some pattern I'm interested in. If you have a pattern that's very localized, then you might want to just use very small convolutions. If you have a pattern that you think it's bigger, then you need to have a bigger one. So it's very problem specific. And it's something, to be honest, that it can be thought of almost as what you might call a hyperparameter, which is something that you sort of just design based on your knowledge of the problem, or basically by searching for a longer range and picking the one that works best empirically. But that's a good question. And just to say one more thing on that. So through a lot of trial and error by many people over the years, people have converged to, at least for vision problems, using pretty small convolutions. So very often you see convolutional layers being simply 3x3 convolutions for 2D problems. So for vision problems, basically. Okay, so one other element I wanted to mention to you folks was pooling. So pooling is an operation that's used to aggregate or to summarize some localized region of your input. Okay, so once again, I'm just showing you the example we just went through. And what a pooling operation does is it takes this intermediate output H, and then it summarizes it somehow into sort of these summary statistics, you can say P of P1, P2, or P3. So this pooling is a function of some localized region A, and two typical pooling operations are either just computing the max over that local region or computing the average over that local region. And so I'm going to show you an example just with the max. So let's say here you had these outputs. So H1 was 0.2, etc. Okay. So what pooling, like max pooling does, it simply takes some localized input, right, of that. So by localized, I mean, once again, it's sparsely connected. So it's not going to be a function of the whole output. It's going to be a function of some localized region here, like, for example, these 3 values. And you just compute the max, right? So the max of this is 1.2. And you do the same. You can think of the pooling as also something that's done by sliding the operation across your intermediate output. And this gives you these pooled values here. So let's look at what happens if we shift the input into the pooling layer, which is the output of the previous layer. So let's see what happens if we shift this by 1 position, right? So let's say we introduce a 0. So we pad it here, and then we shift everything down, right? So this is shifted in this direction. So, and then we look at the pooling now. So then we see that the pooling actually hasn't changed that much. So if we compare it to the previous value, we see that only one value has changed, and it hasn't changed by that much, okay? So what this implies is that, this allows us to have a bit of translation invariance, which means that if our input shifts slightly, it doesn't change too much the output after pooling, which is nice because very often we have problems where, let's imagine you have an input image. You don't want the output to change drastically if you've shifted the input somewhat, because normally, for example, if you have a classification problem, if the image is slightly shifted, it doesn't change the classification value. So this notion of translation invariance is very useful. Another interesting property is that it can be used to compress the signals. So very often when you pool, you get a bit of redundancy in your outputs. So you can see, for example, here all the values are the same. And when you tend to have this redundancy, you can do some subsampling, which allows you to kind of compress your output.
So a question, what's the benefit of using the mean for the pooling operation? Wouldn't you lose information by doing so?
Yeah, you do, which is why average pooling is, it's used sometimes. Actually, it's used in some cases. So the benefit of it basically is that very often you need some kind of summary statistic. And an average is a decent way to do it, but it's certainly not the best. So there are many works that try to find better ways to pool things rather than averaging. But normally it's very beneficial to have some kind of summary information of a set of a set of, for example, vectors, or in this case, outputs. Why? Because, for example, let's say eventually, let's say you want to have, for example, a classification, right? So you have an image and you want to output a classifier score. You're going to need to summarize that somehow, right? So, and basically having successive sequences of poolings along your computation allows you to have some sense of aggregation of local evidence. And the question really is average the best way to do that? In most cases, it's not, but it's useful for some applications. So once again, this is something that people take a lot of time to design these things and to do empirical experiments, and simply based on empirical results, they might choose one versus the other. So basically it means that it's something you try, and sometimes you run experiments and it works well. Sometimes you can do a bit better than simply just trying everything and seeing what works. Sometimes you have some sort of prior knowledge or prior beliefs that tells you, actually, I think in this case, then using a max function is better than an average. But often we don't know.
And then a follow-up question is, the end term in the pooling example seems to be less representative than the center values. Does this affect our results?
It's not perfect, right? It's not perfect. So, and once again, this is a very poor example. In general, it tends to be a pretty decent, a good enough approximation of your input signal, right? So it depends on whether it's more important to have fidelity to your input or to have a more compact representation. And once again, these are things that can play off of each other. So maybe in this case, maybe for this application, it's a kind of okay. You need a very rough estimation of the signal. Maybe in some cases you lose too much information. So it kind of depends. This might not be like the best example, but in general, pooling, if it's done at the right moment, it should summarize your information without losing too much of it. But it's definitely true that it's usually the case that this compression is lossy. You're not going to get lossless compression by pooling. Okay, so I think now you guys have a pretty good view of what a convolutional layer typically looks like. One last element that's missing is the fact that typically when you have a convolutional layer, you don't just have one kernel, right? So let's go through kind of like a slightly more realistic example of a convolutional layer. And I need to go way faster. So let's imagine you have an input to a convolutional layer that looks like this. So you have like this tensor that has this width W, a height H, and a depth D. And let's imagine you have this 1-by-1 convolutional kernel, which is what you're seeing here in yellow, right? So this is this vector in yellow that's overlaid onto your input, right? So you can think of the purple bit as your input I, and you can think of the yellow vector as your kernel K, okay? So when you perform the convolution, once again, you multiply this vector by the region, the non-zero overlap, right? And then you integrate to give you an output, and then you start to shift your kernel. So you shift it down, down, down. And as you shift also across the width, then you get this output feature map, right? So this is completely analogous to the feature map I showed you before. And then now, with your typical convolutional layer that you find in a ConvNet, you have multiple filters, right? So you might have C different filters. And so you apply the same operation C times with these C different filters. Okay, but when I say filters here, but I mean kernels, so they're used pretty interchangeably. Right, and so what this gives you now is this output with a depth C, right, where the number of feature maps you have is the number of filters that you applied. And yeah, and that's like a more typical, a more realistic convolutional layer that you would find. And then one last element is that's typically applied is this nonlinearity, okay? And so I'm going to go into what that is now. So nonlinear activation layer. So they introduce nonlinearities into the computational graph. So this means that the graph can't be easily reduced to a single layer, okay? And this is really crucial, as I mentioned earlier, for like the expressivity or the flexibility of these deep networks. So what are some typically used functions? I'm showing you here 3 common ones, but there are many, many, many more. The first one is a ReLU function, which is just a rectifier that leaves your input unchanged or maps it to 0 if the input is less than 0. We also have a sigmoid function, which maps the input scalar value to a value between 0 and 1. Then you have your hyperbolic tangent that maps an input value, any arbitrary real number to a value between -1 and 1. So these are all like typical functions you'll come across. And so now we have kind of like all the elements. We have like a fully connected layer potentially, we have a convolutional layer, we have pooling layers potentially, and then we have nonlinear functions. Okay. And so these
two questions. There are two questions on pooling. What are techniques for lossless compression, if not pooling? The second one is, what kind of effect does pooling have in pixel resolution, frame rate, and general image processing quality?
So lossless compression. I'm not sure. I'm not aware of any lossless compression methods that are used in convnets. So I mean, in classical signal processing, there are lossless compression paradigms. I can't think of any algorithms now off the top of my head, but I can tell you they do exist. I'm not aware of any that are used in convnets. And then the second question, can you remind me?
What kind of effect does pooling have in pixel resolution, frame rate, and general image processing quality?
So pooling, the thing with pooling is that typically when we have an input image and we have an output, very often the output is not another image, right? So if we're interested in estimating functions that take an image and output another image, so-called image translation problems, then it can have an effect. And in these types of problems, the architecture is designed in order to have as little pooling as possible. Okay, so for example, if you think of images that do like, or models that do pixel to pixel translations or super resolution, you will have much less pooling, okay? If you have a problem where you're trying to classify an image, then you're going to go from a full input image into basically, you're mapping this to an output, which is a vector of probabilities, right? Where, for example, if you're classifying, if you have 10 classes, you have 10 values at the end. So necessarily, you're going to be compressing your representation. At the end, your representation of an image is going to be a 10 by 1 vector, right? And in that case, some form of compression is inevitable, right? And in that case, very often, these models use pooling layers, different types of pooling layers, in order to achieve that. So it really depends on the type of problem you want to do. Okay, so putting things together, typical deep networks chain all of the elements, all of the building blocks I just described, right? So I mentioned 4 building blocks. We have fully connected layers, convolutional layers, pooling layers, and activation layers. And so these are chained together in order to give you some sort of deep network, okay? I'm including here the last, this connection, which is called skip connection or residual connection, just to indicate that you don't necessarily just have this simple chain of events, right? Very often you can start to have very complex graphs. So we're really running a bit out of time. So I think I'm going to skip this, unfortunately, and move into loss functions. Can I ask a question? Is it necessary we do a break? Chianti, what do you think?
I mean, I think like since we're sort of like a little behind in time, I think it's okay to just keep pushing forward.
Okay. And given that people are asking questions off the bat, it's good.
Yep.
All right, so let's keep it moving. So next up, let's look at loss functions. So we've just described how we can create some sort of architecture or model, right? But remember that ultimately what we want to do is to have a model that estimates a function, right? And so the first thing we need if we want to estimate a function well is to understand how good is it, right? To have some measure of the performance or the accuracy of this model, okay? And this is where loss functions come in, okay? So yeah, put another way, just recall this equation from earlier in the presentation, where we have this function that is, we're trying to estimate some given function, where we don't know the function analytically at all, but we only have pairs of inputs and outputs, okay? And we would like a measure of model fit, of understanding how close are we to achieving this, okay? So one example of this is the squared error. You'll come across this a lot, where let's imagine these are real values. Okay, so let's say we have a regression problem. This is one very reasonable and intuitive way to measure how close are you, right, to the target. Of course, this is just for one example, and so it's not going to be very robust, right? If you have a model, let's say you have a model that's trying to estimate, given an image, how professional it looks. Let's say, for example, let's say like on a scale of 1 to 10, you say, okay, I think on a scale of 10, this was done by a professional photographer versus I think this was done by an amateur. Okay, this is something you can give a real value to. Okay, and if you wanted to have a model that modeled well this problem, this function, this mapping from input image to degree of professionality, then measuring your fit with respect to one sample is not very robust. Okay, so you want to have some sort of population measure. And so typically what people do is they use functions which are computed with respect to some representative sample of your data distribution. Okay. Yeah, so for example, what you might do here is instead of using the squared error, you would use the mean squared error averaged over some representative sample of data. And this is typically termed a cost function. So one important detail here is the concept of datasets and dataset bias. Okay, so when we're training models and when we're evaluating them, the data on which we evaluate and train is critical, right? All of this, as we know, the data is a fundamental element of this whole training paradigm, right? So if the sample that we're using is not a good estimation of the data distribution that we expect when we're deploying our model, this means that any fit that we estimate is going to be misleading. And this means that the model can be deployed with the understanding that it works well, whereas it doesn't. And this can cause very severe harm, right? As been shown by work, for example, from Boualamwini and Gebru in 2018. And as we've all seen, I think, with recent news, for example, with facial recognition technology being used inappropriately and resulting in people being actually arrested wrongfully. So it's very important to stress the fact that all of this is dependent very much on the data that we use. It's a key part of anything that we do with all machine learning. And so it's something that we have to understand very well, the biases inherent in that data. So with that being said, how do we choose the right loss function? So as you would imagine, any loss function should be well tied to the task that you want to perform. And so there are, a plethora of tasks you can think about. For example, we have regression problems. So I gave you an example of one before. We have classification, as I mentioned, like classifying images. We have ranking problems. So we might want to say, given an image, I want to rank a set of other images with respect to how similar they are to my query image. Okay, that's an example of a ranking problem. And then you have problems related to sequence prediction and clustering, which I won't cover for this talk. I'll just give some examples for these top three, which are most classical. So I showed you before this error. So this is the squared error between some outputs, predicted output, and your target. So this is actually not necessarily used that often because it's very sensitive to outliers, right? So you can see here, for example, as this difference increases, it's quadratic in terms of the difference, right? So if you have a big difference, you have a very big loss, which sometimes is not it's not great when you have outliers. So people very often use the Huber loss, which regresses or degenerates, you can say, or results in the squared error for distance values that are less than some threshold. And if it becomes large, if it goes over delta, then it's no longer a quadratic function of the distance, it's just linear, okay? So this allows us to temper somewhat cases where we might have outliers. This is used very, very widely in deep learning. We also have classification error. So the canonical one here is the multi-class cross entropy, also known as a negative log likelihood. And so what this is doing is it's giving you a measure of a difference of two probability distributions. So you have on one side the distribution of your target labels for classification, and then you have the distribution of your predictions. And what this is measuring is how different are those distributions. And so minimizing this loss will minimize the difference between your distributions, which is what you want. Okay. Then lastly, we have ranking. So one example, and among very many that I could have chosen, but I'm choosing this one because I think it's very intuitive, is what is called the triplet loss. So this takes as input some triplet. So here I'm showing you YA, Y plus, and Y minus, where YA is considered an anchor. And then you have Y plus and Y minus. So what the triplet loss wants to do is it computes the distance between the anchor and the positive, and the anchor and the negative. And what we want is that the distance between the anchor and the positive element is smaller than the distance between the anchor and the negative element. So what this does is that it ensures that if you have an anchor and if you have some element that ought to be closer to it, so for example, ought to be more similar to it than some other negative sample, then you want to enforce this basically. And that's what this loss is doing. So it's telling you basically, I compute the distance between my anchor and my positive, my anchor and my negative, and if they're not sufficiently different by some margin, alpha, then I'm going to incur a loss. Okay, so this is one of many loss functions that can be used for ranking problems. Okay, so that's kind of like the last piece of the puzzle in terms of the bits we need here for the forward performance, right? So we have our model, we're given some output, we have a target, and we compute a loss. Great. So now we know what our model is. We know we have a measure of how well it's performing. And so now how do we improve performance, right? So this is where optimizing deep models comes in. So as I mentioned before, so we have a set of weights, right? So I'm going back here to this example of a linear layer, a fully connected layer, where we have this weight matrix W. So we haven't talked at all yet about what these values are and how do we set them. And this is what I'm going to talk about now. So two ways to do that, two major paradigms are on one side, gradient-based approaches, and another side, approaches which are gradient-free, but I won't go into those for this talk. So basically the dominant paradigm for training neural networks, for setting these weights, is what we call gradient descent, which some of you may be familiar with from more like optimization-based classes. And so what this algorithm does is it minimizes some sort of function, in our case, a loss function, by sequentially updating the weights with respect to the function that we want to learn. And it's important to note that given that deep models are highly non-convex, we're not going to get a globally optimal solution, but we will be able to get a locally optimal one. And lastly, it's important to note that because we're doing gradient descent, we need to have functions that are at least piecewise smooth. And if you think back to all of the building blocks of the computational operations that we've discussed previously, so we've discussed matrix multiplication, we've discussed pooling, we've discussed convolutional layers and nonlinearities. All of these computations, which form the building blocks of our deep model, are look at least piecewise smooth, right? So this means that we can compute derivatives. So here I'm going to take like a very toy example of gradient descent just to give you some intuition about it, if you're not already aware of it, taken from Goodfellow et al.'s excellent book. So here, let's say we have this function, f of x, right? So here is this quadratic function here in the dashed blue line. And let's imagine we don't actually know the analytic equation for this function, right? What we do know is that we have x, and then we have the output f of x, but we don't know what the function is. Let's imagine that's the case. And let's imagine we're able to compute the gradient at this location x, okay? So, and just for reference, the gradient, of course, is the straight line here, okay? The green line. So what gradient descent does is it says, okay, if I have this information, what I can do is compute the gradient at this location here. And if it's positive, and whatever that gradient is, of course, the multivariate case would be a vector, then I go in the opposite direction and by some small factor. because I don't know how, I need to go in the opposite direction, but I don't know how far I need to go. So I'm going to take like a small step. Okay, I'm going to take like a step epsilon in the direction I need to go in. Okay, so let's imagine you start here. You say, okay, I compute the gradient. It's increasing in this direction, so I need to go the other way if I want to minimize this function. Okay, so then you might take a small step here. You compute the same. You take a small step here, and you keep going until you start to get in this point where you don't really know what to do, and then you kind of say, okay, I'm more or less at the minimum. You can do exactly the same thing on the other side. So let's imagine you start here. You say, okay, the gradient is increasing, the function is increasing in this direction. So if I want to go downhill, I need to go in the opposite direction. And I start to take some small steps until I get there. Now, I'm saying small steps because if we took huge steps, we might start to do, like, we might start to have some degenerate behavior, where, for example, we might take a huge step, and then we end up on the other side, and then we take another huge step, we end up over here, we take a huge step, we end up over there. And so we might be stuck forever doing this, right? So what we want to do is to kind of carefully take some steps so that eventually we kind of end up in more or less the right position. And so this step size it's a hyperparameter that's it's probably one of the most sensitive things that you have to tune when you're deciding, when you're training your model, right? You spend a lot of time trying to find the right, what we call learning rate. So this just kind of summarizes what I just mentioned. So let's say you have some function y, which is f of x. You compute the derivative with respect to x, and this gives you the direction that you need to move x in order to decrease y, right? So in other words, if you have some function f of x, if you want to decrease this value, you need to shift x in the direction opposite the sign of the gradient, okay? And then you need to shift it by some small, scaled by some small epsilon number. And that's basically gradient descent, right? So in our case, I just showed you a very toy example, right? But in our case, exactly the same thing applies, right? But in our case, what we like to do is to change w, right? So we don't want to change x. We want to change the weights w so that our cost function is minimized, okay? So we have some sort of cost landscape that's computed over an entire training set. And we would like to find some local minimum of that cost function by modifying x, by these small sort of sequential updates to w. Sorry, by modifying w. So as I mentioned, I might have mentioned this before, but if not, so many cost functions that we use in machine learning can be decomposed into a sum or an average of the loss with respect to an individual sample. What that means is that we can express our cost function as a summation over the loss, some loss function. For example, any of the loss functions I just was describing before, with respect to a specific sample, a specific pair, right? So we have x of I here, t of I. We compute the output with respect to x and parameterized by w. We compute the loss with respect to our target, and then we sum or average this to give us our cost. And so given that we can compute this cost, right? So this difference between what we want and what we have, right? So this loss with respect to our target, then we can use gradient descent to update the weights in exactly the way I just described before, right? So we can have a gradient estimate, which is an average of the gradient estimate with respect to every individual sample. This gives us a gradient estimate for the entire model. And then we use this gradient estimate to shift our weights. So to go down the hill of the loss function with respect to the weights. Okay, and then once again, we're going to shift by a scaled factor, right? By this factor epsilon. So we don't take steps that are too big. So one thing to note is that this can be pretty expensive to compute, right? So let's imagine you have a data set that has millions of examples, right? Which is very reasonable. Let's imagine that at every step we wanted to take, and very often we take steps, we might take hundreds of thousands of steps, right? But when we're training our model, if at every step we need to compute this gradient by computing it over 1 million examples, that can be extremely computationally expensive. So typically we don't estimate this with respect to the whole training set. we estimate it with respect to some sample using what we call stochastic gradient descent. And so I'm going to describe that next. So this is extremely simple to what I just described before. There's pretty much just one major change, right? So let's just go through it. So we have some sort of linear rate schedule. So these are these epsilon values that we use to make our steps. We have some initial parameterization W. And then in a loop, so we do this iteration where we make these sequential steps. What we do is we sample some mini match of examples from the training set. We compute our gradient estimates. And then we use this estimate to shift our weights in the right direction. Right, so really the only change I mentioned here with respect to gradient descent is that we're using this sampling of over the training set as opposed to using the whole training set. And so what this means is that we can have, once we have a good enough, and what is good enough is, you know, there's a lot of, this depends on many factors, right? So this is once again something you have to figure out often by trial and error, but sometimes there are some theoretical results you can use to help you decide what's a good how to choose a representative sample. But once you have such a sample, you could use that instead of having to go through the whole training set. And so one last thing to mention is that, so we have to start off with some initial parameterization of W before we can optimize it. And for deep learning, you know, because it's a local, we're going to compute just a local minimum, where you start off is quite important, right? So in practice, what people typically use is they initialize your parameters by sampling from some distribution. Most typically, it's either a uniform distribution, so the uniform distribution between 0 and 1, or a normal distribution with a mean of 0 and a standard deviation of 1, for example. These are very typical distributions that are used. Okay, so some of you might be thinking, that's all well and good, but how am I going to actually compute this, right? This looks extremely non-trivial to compute this gradient, right? So this is really the key thing that we need to do to be able to actually apply gradient descent. So what we use is an algorithm called backpropagation. Backpropagation of gradients, or simply backprop. So this is a pretty straightforward application of the chain rule from calculus, in which what we do is we compute the gradient of L with respect to each weight in the network in a recursive fashion. So starting from the final layers and working backwards. Then once we have those gradients, we use gradient descent, as I described before, to update the weights. And so in this way, by this recursive computation, as you will see, it can be used for quite complex networks once they're comprised of piecewise smooth functions. And lastly, and very, very importantly, it's pretty simple to implement. And you will see that it can be inexpensive to compute for some reasons I'll describe in a bit. So before we get into backprop, I just want to remind you guys of the chain rule with some very simple univariate examples, but they extend very easily to multivariate functions. So let's imagine you have a function, a y, which is a function of u, and you have u, which is a function of g, of x. U, sorry, is the output of a function g of x. Okay. Then this is, this chain rule simply states that you can compute the gradient of y with respect to x in the following manner. Okay, by the simple product. And you can extend by exactly the same reasoning to compute the chain rule for a much longer chain of computations. Okay, so let's say you have sort of this very long nesting of functions. You can, in the same manner, compute y of x as this using this product rule, this product of derivatives. Okay, so with that in mind, let's take a look at the backpropagation. So there are 4 main steps. So you perform what is typically called the feed-forward computation, where you go from input to output. Okay, then you perform backpropagation from the outer layer, so from the loss function to the final layer, and then you recursively backpropagate through the inner layers, and then as you go, you update your weights. So let's look at this through an example. So let's say we have an input function, very simple one, just three values. Okay, you have a fully connected layer with these weights, right? This weight matrix W. Then you perform some sort of nonlinearity that gives you your output vector O. And let's say you have a second layer. In this case, this is a 3 by 1 layer. So you just have one output, but it also has these weights, right? Just 3 weights. You compute another nonlinearity, and this gives you your output here, okay? And let's say you want, you want these two to match. So this is your output and this is your target, and you compute, you compute your loss using this loss function L. Right, so this is the forward computation. And the first step in backpropagation is that you can compute all of these derivatives, right? With respect to different variables. So for example, starting from the outer layer, you compute the derivative of the loss, or the gradient of the loss, well, the partial derivative of the loss with respect to the output. And then you can compute the derivative of the output with respect to the input, this hidden output here, H, okay? And then here as well, you can compute the derivative of H with respect to either the inputs to this function, right? So O, or with respect to the weights, right? So you can compute these two partial derivatives here, okay? And going further, you can compute this, the derivative of O of 1 with respect to, for example, H3, and you can keep going, right? So you can compute all of these partial derivatives all along your chain of computations. And then by applying the chain rule, you can simply compute the product necessary for you to get the gradient that you need, right, to update your weights. So for example, let's say we wanted to update this weight here, okay? What we would need to apply gradient descent would be to estimate this, okay? And using the chain rule, we can compute it as this product, right? As you can take a look and you can see it here. If we wanted to go further and we wanted to compute the loss, we wanted to update this weight, we would need to compute this loss. And we can do it by just, collecting like the partial derivatives that we need and then computing them using the chain rule. Okay, so this is in a nutshell how backpropagation works, to allow you to start from the loss function and collect recursively the derivatives that you need to eventually compute the loss with respect to a specific weight at any arbitrary point in your computation. So let's just go through like a very quick example here. So let's imagine that the loss we're computing is the squared error, okay, the squared loss. We compute the derivative with respect to the output O2, so which is simply this. Then let's say we're computing the output, the derivative of O2 with respect to H2. So in this case, let's imagine this function is the sigmoid function, okay? Then the derivative is simply this. And then lastly, we need to compute the derivative of H2 with respect to, for example, the output 1j, okay? Which is very simply this. And if we wanted to compute it with respect to the weight, it's simply that, okay? So we have all these partial results, okay? And then we just combine them in order to get, by multiplication, in order to get the gradient that we need. And then once we have this, we can perform gradient descent, stochastic gradient descent, as I described earlier. So one point, I talked previously about computational efficiency. So where that comes in is that you can see, for example, if you look at the computation, let's look at the computational path, right? The path that we need to compute the derivative of the loss with respect to this weight, right? W133. You can see here that we need the gradient with respect to certain partial derivatives, okay? Certain intermediate outputs, I should say. So if you look here, you can see that, for example, this is one partial derivative that we need. And the output of what this results in is actually an intermediate representation from the forward pass, right? So it means that in order for us to compute this in the backwards pass, in the backpropagation step, if we kept this, if we cached this intermediate result, that we already computed at training time, then we simply need to just look it up and plug it in, okay? So if we're able to cache intermediate results, such as this one here, we can use it when necessary to compute gradients during the backpropagation step. So this allows us actually to reuse a lot of computations that we use in the forward pass at the cost of having to cache intermediate results. So I'm going to go quickly over this. So we more or less have all the elements needed for learning deep models now. One last thing I want to mention is the fact that deep models typically need regularization. So what does regularization mean? So we have to understand that deep models are often very parameterized, right? So your typical modern deep model has millions or sometimes billions of weights, okay? And so what that means is that just as in machine learning, for those of you who are familiar with it, they suffer very greatly from an overfitting problem. So this is an illustration of overfitting. So let's say you have a classification problem where you want to learn a decision boundary, i.e. a classifier between these two classes, right? Red dots and blue dots. So you have two options here, right? So you have like the black line, which is one option for the classifier, and you have this squiggly green line. So what you can see is that the green line, it is actually separating these classes perfectly, right? But it's using all of its kind of flexibility given by the fact that it's very parameterized in order to be very tuned to the specific examples we're seeing here. But as we mentioned before, when we're learning models, we don't have access to the entire data distribution. We have access to some sample of this distribution, which is what we call our training set. But our training set does not equal the entire distribution, right? And so every time we collect a training set, we will get slightly different samples. So let's imagine that we were instead training with a slightly different data set, right? So if you look, you can see that I made very few changes to this data set, but you can see that now our model, which was perfect before, is making a lot of errors in the second stage, right? And so this is overfitting in a nutshell. It's the fact that you have so much flexibility in your model that you're fitting the data at training time too closely, but you're not generalizing to data from a slightly different but realistic sample of your overall true distribution of data. Okay, and this is actually it's a huge problem for deep models, and it's something that regularization is critical for addressing. And once again, this is a pretty active area of research. There are many different techniques that are used, some of which I list here. What I'll just mention is a very intuitive one called early stopping. So the way early stopping works is that you, at training time, when you're going through stochastic gradient descent and you're at periodically updating your weights, when you're doing that, you keep like a validation set of data, basically. So this is going to give you like a what you might call a held out set of data that you can use as kind of like an independent verification of the performance of your model, right? So you can say, okay, my model is learning, I'm updating it sequentially, and it's performing really well. And actually, I reached a point where I have zero loss. It's perfect, right? If you take this model and you compute performance on this held out validation set, if your model is learning well, then initially your performance on this validation set will also improve, right? So your loss will also decrease. But there will likely come a time when the performance on your validation set will start to degrade, okay? Even as your training loss is improving. So this is an indication when you start to see a deviation between the performance on your validation set and on your training set, this is an indication that your model is overfitting. And so what you can do is what you call early stopping, which is when you start to see that happening, you just basically stop. And you say, okay, at this point, I think if I train it any further, it's not going to be useful. It's not generalizing to this validation set. So I'm going to halt my training here, right? So that's one way to do regularization, but there are many others. So I'm kind of, this is it, this for our main introduction to deep learning. So before I go into some applications, what I wanted to do is kind of show you some key milestones in how we came up with all of these building blocks. I mean, we as a community, how we came up with all these building blocks that led us to the deep learning models that we have today. Okay, so I think one reasonable place to start off is with in the 1940s, where McCullough and Pitts first presented what you might call like a neural network as you might recognize it today. And then in the 50s, the perceptron was introduced, and I think I skipped this bit, but this is very important. Sort of introduction of the concept of a unit, of a neuron, or of this hidden unit in these deep networks. And this was quite inspired by neurons in the brain, as the name suggests. Then in the 1970s, backpropagation was used by Lin and Ma. And then it was combined also in the 70s with neural networks in order to train, to adjust weights, basically. So use in the way that we use them today. Later on in this decade, so the neocognitron was introduced. So this is really what you might consider to be the first really deep neural network. And in the 80s, the ConvNet LearNet was introduced by LeCun et al., which was the first to kind of combine neural networks with backpropagation effectively to train a recognition model. And then, there was quite like a split in time where basically kernel methods ruled. But during that time, well, I should say later on in that time period in 2009, ImageNet was published, which was the first of its kind in terms of the scale of the data that it contained. And then a few years later, we have like quite a watershed event in 2012 where AlexNet, this deep model, won this challenge very convincingly. And so you can see that basically with time, we started from loosely biologically inspired networks of computation, understanding, then plugging in backpropagation to be able to kind of train these weights and then applying them to practical problems. So this recent revolution, which we've been living through for the past 10 years or so, is due in very large part to having large-scale data. So as I mentioned before, I haven't talked a lot about data in this talk, but it's really such a crucial part of modern deep learning. We also have, of course, hardware accelerators, so GPUs most notably, and some key architectural breakthroughs. For example, understanding that ReLUs can be quite effective for being able to translate gradients backwards through time, through computation, I should say. So I am going to, unfortunately, I wanted to talk a little bit about analyzing deep networks, because of course, there's often a lot of talk about the fact that deep networks are in some sense black boxes. But since then, there's been, over the past years, there's been a lot of strategies for probing deep networks and understanding what these weights are learning and what these computations are doing. And so it's a very interesting area of work. I'm going to skip through it in the interest of time, but I have some references here.
We're fine with you going over about like 15 minutes. So instead of going to like 11:30, going to like 11:45. That's okay.
Okay. Well, in that case, let me. Okay, sure. Okay. So yeah, I just put a couple slides in here, but I just wanted to say that, to mention a few common strategies for probing deep networks. So just to list them out, so in some way you could visualize the activations. So I kind of did this earlier on. If you think about the very toy example I showed up quite a few slides ago, where you had the heat map, the black and white map of your input signal, your kernel, and your output, the output of the convolution. So visualizing these types of activations is one way that you can sort of probe a little bit what your deep network is learning. Another thing you can do is to not look at the activations, but you can look at the weights themselves, if you can visualize it. What you can also do is get a sense of, you can sort of backtrack through your computation. If this network has a specific output, what are the input regions that maximally contributed to that output? Okay, and I think I'll show you an example of that in a second. Another thing you can do is to visualize the learned embedding. So I use the term embeddings here, but this is another way to say intermediate representations. Another thing you can do is to visualize the gradients themselves. So it's try to understand in what way should these weights change in order to affect the output. And another thing we can do to kind of understand what deep networks are learning is to investigate adversarial examples as well. So I'm only going to show you one example of this, which is the example, one approach to studying how deep networks learn or what they learn using by simply deforming an input image and understanding how that deforms the output. So if you look here, so this is work by Naila et al. From a few years ago. So let's say here you had a classification model, okay? And what you can do is you can compute a heat map that's shown below that shows you what are the regions of the image that are maximally activated by this learned classification model, okay? And then what you can do is you can say, what happens to the activation if I basically scramble or introduce noise into some local region of the image, right? So let's say you have this image of a Pomeranian dog and you introduce noise into this little square block here. What you would expect is that a good classifier should not be super impacted by that, right? However, if you were to put this square over the face, then the output would change dramatically, right? Because at this point, you're losing a lot of information that would be critical to be able to accurately classify the image, right? And so this is an intuition. And so what this work did is that it did exactly that. So it took this square like noise patch, you can say, and it basically computed like a sliding window, let's say, of this patch over this image, right? So I shouldn't say compute a sliding window. I should say it introduced noise at different regions of the image, okay? And then what the output here is showing is it's showing you the response of the classifier to this image given where the patch is. So what you can see here is that if you have a patch that's in this region of the image, it doesn't affect the output of the classifier, right? It still signals very highly. So red means that it's giving a high signal for the image. So it's saying that if a patch is here in the input image, I'm still going to label this very confidently as a Pomeranian. However, as the patch starts to go towards the center, so you can see here, the labeling as a Pomeranian goes down dramatically, right? Which is one way to probe and to kind of confirm the intuition that the deep network it's paying a lot of attention to this region of the image, right? So if we remove this from the input image, it is no longer able to accurately classify this dog. Okay, which makes a lot of sense. So this is just one example of ways you can kind of probe your network to understand what it's doing. Another one is to reconstruct image patterns from highly activated neurons. So it's in a similar sense to this one, but what it's saying is this. Okay, let's assume we have a learned network, okay, and we want to take one neuron. Let's imagine a neuron from one of the higher level layers, and we want to create an image pattern that would excite this neuron, and I'm using here sort of like neuroscience terminology, but would give a very high response to this neuron, okay? And so that's a way of telling us, what is this neuron looking for, right? What kind of pattern is it trying to match? And if you do that, so if you take a neuron and you try to change your input such that this input maximally excites this neuron, then you can sort of get a sense of what has it learned to look for, right? And so if you look at these results here, you can see, for example, that this is showing results for different layers of a deep network. And you can see that for the first layer, for the layer 1, here you're showing these are the learned weights. Okay, so you can see there's a sort of 2D pattern. And if you construct images that would excite this neuron, you can see that it finds these are the types of input images that would maximally excite this neuron. So you can see that it's basically images with like some sort of color gradient with some sort of orientation, right? And as you go higher in the layer, so for example, this is layer 2, you can see that the types of patterns that activate these neurons become increasingly complex. So now if you look at layer 2, for example, these are some of the neurons. These are like visualization of the weights. And if you look at some of the images that excite that neuron, you can see that it starts to be, things that look maybe like eyes or some complex circles, curvature instead of edges, etc. And you can see that these patterns that the neurons are looking for are increasingly complex as you go through the network. So I have to say I'm choosing a lot of examples from computer vision, but this is because this is where probably it's most easy and most intuitive to probe deep models. But that being said, I mean, there's also quite a bit of work in, for example, natural language processing that does these types of probes as well. Okay, so
there's a question. What happens when the derivative is undefined at the origin, or the derivative of the ReLU function is undefined in backpropagation?
Yeah, so this is it's a good question. So normally it's sort of ignored. So basically deep learning uses the concept of subgradients more than gradients directly. So it's sort of an area that of course is undefined and it's just treated as such basically. So if you were to have something that was actually computed at this point, you would have an issue. But in general, you're able, because it's at least piecewise smooth, you're able to use subgradients to backpropagate all the way to the beginning. So the answer basically is that we just use some numerical gradient techniques in order to use subgradients instead of gradients to backpropagate through these piecewise smooth functions.
And I also wanted to give you a time check. We're like at 11:28.
Right. So I think I'm going to go over by maybe 10 minutes. So I'm just going to go very briefly through applications in computer vision. Okay.
Okay. Yep.
Okay. So thanks everybody for sticking in this long. So this is sort of the end here. So I think I've given you guys like an overview of deep learning as a whole. So I just want to give you a sense now of how are these models really used for computer vision problems. Okay. So I've mentioned classification a lot. So I just want to give you kind of like a flavor of what these types of modern classification models look like. So here you see like a very influential one from a few years ago called VGG19. And as I described earlier, these are really very deep models, but comprised of exactly all the very simple building blocks I showed you before. So here we have like a 3x3 convolutional layer with 64 filters. So if you remember, I showed you this example where you have like multiple filters that give you feature maps, a set of feature maps C, right? So this is exactly what this is describing. So you have a 3x3 convolution over your input image, and you have 64 of them, right? And then you just stack all of these. And this is implicit here, but all of these have nonlinearities as well, included in after each one of these. At certain points, you have pooling functions. And at the end, this is very typical for classification problems. You have like a couple of fully connected layers, one or more fully connected layers. Okay, so this is like a very classical paradigm for a deep model for classification, especially for image classification. And a more recent, oops, I went the other direction. So a more recent example has even deeper layers, right? So in this case, we have 34 layers, and like the best classification models now have like 150 layers, for example, right? Typically. But once again, they're all using the same building blocks, right? So in this case, they're just deeper, basically. Another kind of recent innovation that has been used, not just for images, but for many, many different types of input signals, is introducing these skip connections that I mentioned before, which allows you to introduce information, so to move information directly from earlier layers of a network to deeper layers of the network. And not just that, but also to backpropagate, because remember in the backpropagation step, we're going to also recursively compute computations from the later layers through to the earlier layers. And these skip connections also allow you to backpropagate gradients also effectively in the backwards direction. So another problem in computer vision that's very classical is object detection. So to describe it, you're given an image and you would like to detect each instance of a set of semantic categories. And this can be at a high level or very fine grained, right? So for example, you can say, okay, I have this input image here. and I want to localize the objects, and I want to give a label to each of these objects. So I want to say, okay, this is an object here, and I know it's a German Shepherd versus a Husky, for example. So one very successful model to do this is called YOLO. And so this, once again, you can see it has a very similar form to the previous model I just showed you, where basically it starts off with convolutional layers, with pooling layers as well. And you sort of progressively stack these convolutional layers until a little bit towards the end, you have these fully connected layers, okay? And so this is the same model I just showed you. And so at the output, what you have is, you have a grid as an output. And this grid corresponds to a grid. It can be sort of like projected onto your input image, okay? And what it's doing is like, it's a tensor that has like a spatial kind of, like some spatial extent. And so what it's telling is that every location in this tensor, at every sort of spatial location within this tensor, I have like a vector associated with that location that's giving me an estimation of bounding boxes at that location and their extent. So it's saying, okay, I think there's a bounding box at this point. It has a certain width, a certain height, etc. And I think it might be, I think within the bounding box, there might be this category, and my confidence is some value, okay? And so your confidence might be high or it might be low, but you're going to make a prediction nonetheless for every location within this grid, okay? And so what you do is you take this collection of bounding boxes, of categories, and of confidences, and you use this to extract your highest confidence bounding boxes and with your highest confidence labels, okay? So this is a sort of like one paradigm for object detection that has been quite successful because it's quite fast. So because it's primarily composed of convolutional layers, as I mentioned before, conv layers are generally quite efficient. It means that if you have a detection model that's composed mainly of them, they can be quite computationally efficient. So you can compute this very quickly. And this is used for a lot of real-time object detection problems. For example, if you want to do autonomous driving and you'd like to, in a real time, of course, detect pedestrians, traffic lights, etc., you're probably going to use something a bit similar to this. A kind of related problem is instance level segmentation. So it's a bit similar to what we did before, but when we have these bounding boxes, we also want to have a per pixel segmentation. So we don't want to just say there's a person in this bounding box, but we want to know which pixel actually corresponds to the person, right? As you see here, for example. And so this is one sort of paradigm for it, where you have, it's a bit similar to the previous one where you compute bounding boxes, but in this case, you simply have an additional branch that predicts some mask, right? So it gives like a binary mask for every detection to tell you within this bounding box, it's a binary mask that says, okay, it's 1 if this pixel belongs to the actual, the object. Another problem is image matching and retrieval. So this is used very widely for all kinds of ranking and recommendation problems. And the problem is the following. So let's say you have this query image, and let's say you want to find similar instances of this image within some potentially extremely large database. It could be a database of billions of images, right? So what you want is to be able to look within this database and then find similar images or images with exactly the same content. So we can use the triplet loss to train a model to do this, right? So this is the loss I described earlier, where your triplet consists in some sort of anchor image, which we call the query, a positive image, which is a relevant one. So it's an image with the same, in this case, the same building, and then a non-relevant image, which has like a different building, okay? And then you can, at training time, you can compute a loss, which is a triplet loss, as I mentioned before, and then you can use this to train your model. So what this means is that at deployment time, you're going to be able to compute representations. So these vectorial representations of these images, which when you compute the distances between them. So if you, for example, you take this query image and then you compute the distance between this image and all the images in your database, hopefully, if your model was well trained, the distances between the query image and the relevant images will be smaller than the non-relevant images. And that will allow you to extract these the images that you're interested in. There's also, the problem of video action activity recognition, which can be sort of loosely described as classification, but for videos, basically. So for example, you can say, here's a small snippet of a video, and it depicts somebody doing a cartwheel. And what's interesting to note about these types of problems is that because you're dealing with, you have a time dimension, you tend to also introduce additional kind of signals. So one thing that's typical is to use not just a model based on your frames, but also a model that tries to represent or try to use information about the motion that's happening within this video. So for example, optical flow is typically computed in order to get to generate representations of the movement that's happening within the image, within the video sequence, I should say. So I won't go into all the details of the architecture, but that's kind of the main idea. And so another interesting point that I think is probably of interest to many people because it's very trendy and very cool is generating images. Right? So here the problem is that we have some sort of input random variable. And just to go straight to the example here, let's say your input variable is z, this is vector. And then you have a deep network that progressively transforms this input variable so that your output is an image, right? And then this is the problem of image generation, and there are many approaches to doing that using convnets and other types of networks. There are two kind of main paradigms for doing this. One is based on GANs, which is the example I'm showing you here, but there are many examples that there are many models that use variational autoencoders. So to continue with this example, so let's say you have this generator. What a GAN would do is it would, at training time, when you have this sort of this generated image, it uses a set of generated images and real images to train a discriminator, which is being trained to discriminate between both, right? So let's say on the discriminator side, you have an image X, sorry, my battery's gonna die. You have an image X, and then you train this classifier to be able to tell you, is this image a real image or is it a generated image? And if you're and so basically these two models, one is a generative model and one is a discriminative model. And these two models are playing this adversarial game where on one hand, the generator is trying to generate images that are so realistic that it's basically categorized by the discriminator as being real, whereas vice versa, the discriminator is trying to be able to distinguish between the two, okay? And so if this game is well balanced, then you can learn very effective image generators. And I just want to show you here that, so you can see that this model, it's comprised of what these call these little blocks, right? So just a few of them before you have this hyperbolic tangent nonlinearity. And I just want to show you that, once again, these blocks, so this is basically the architecture for one block for the discriminator, that once again, there's no mystery behind them. They're composed of the simple kind of building block functions that I described before. In this case, ReLU functions with 3x3 convolutions. Another problem is image translation, where, for example, let's say you have an image that was taken in the summertime, and you'd want to kind of like translate it to what it would look like potentially during winter time. That's another kind of problem. This is what I was describing before as these kinds of like image translation problems. And in this case, as I was mentioning before, I think I skipped, yeah. As I was mentioning before, because we're dealing with a translation problem, we would have typically a model that tries its best not to pool too much, right? So for example, this K going to K2 going to K4, if I remember correctly, I think this has to do with the amount of pooling that's happening. And as you can see in this case, the pooling is relatively limited, right? Because in this case, because you eventually want to output another image, you don't want to lose too much of the fine-grained information. And yeah, this is basically the discriminator, which is typically used in these problems as well, to be able to say, okay, I want to be sure that I can't tell that this was an image that was translated, for example, into being a winter image, or whether it's a real image taken during the winter. So the same kind of adversarial approach can be used for translation as well. And lastly, I wanted to just mention briefly self-supervised learning, because I think it's something that's, it's a very recent development, I would say, in terms of being used successfully. So I think it's worth mentioning. So this is, throughout this whole talk, I've been talking about about supervised learning, where we have as input pairs, right? So we have an input X and an output T. So what happens if we don't have T, right? So this is actually the typical case for, learning problems, because having T is actually quite expensive, right? So let's say, for example, you have a classification problem. Having T would mean that for every input image, you have a label for that image. That means like some human most likely has to go through every image and label it as belonging to some category. And that can be quite expensive to collect. So it'd be really great if we could do more learning with less annotations from humans. And this is where supervised learning has been very successful recently for different areas, including computer vision. So the way it works basically is it computes kind of annotations that you kind of get for free, right? So for example, what this particular work, SimClear, is showing is a supervised learning, self-supervised learning framework, where as input, you have an image, you have some function. In this case, it was an image. You have some input, which was an image in this case. And what you do is, what you know about it, the target you have is that this is a specific image, right? And so what you can do is you can compute some augmentation of that image, which is depicted by this function here. It is a transformation of the image, right? To give you two versions of the original image. So given an input image, you have these two versions. They're changed slightly, like maybe they're cropped slightly differently, or the color has changed slightly differently. And then you compute some representations of these augmented images. And then what you want to do is you want to ensure that the similarity of the representations of these images are similar, okay? And so the target you have here is a similarity target. So it's in a sense, it's a bit similar to the kind of the triplet loss function we described before, in the sense that what you do know is that I don't know what's in the image, but I do know that these two versions are versions of the same image. And that's what you use to supervise your learning of this representation. And this has been proved to be a very effective way of learning representations that are sort of generally useful. And then they can be kind of reused for many different types of so-called downstream tasks. Okay, so I've reached the end. I just wanted to recap where we've been, right? So we started off with understanding what's deep learning. We went into sort of understanding how do we design deep models and with what kind of building blocks. We looked at what are loss functions and how can we use them to measure model fit. Then we discussed how can we use this to optimize the weights for our models to improve fit. And then lastly, I just gave you kind of like a brief tour of some applications for computer vision. So that's it. Thanks for sticking around. Oh yeah, I just want to mention I have some references here for you. So yeah, thanks so much. And I'm happy to take any more questions if we have time.
Thank you so much for the introduction to deep learning. I want to let everyone know that we have office hours now. I know that this material was quite dense and you guys first time seeing it. So we created 2 additional office hours. So we have 4 office hours. Please go to office hours if you have any further questions or just you want to like sort of chat about some of the material that we covered today. Yep. And thank you again. We really appreciate it.
Yeah, happy to be here. Take care.